Hi, my name is Bahadur Ahmedov. In this video lecture, we are going to start our discussions about the eigenvalues. So essentially, in this video lecture, we are going to talk about what is the eigenvalue and eigenvector, and we will try to figure out the eigenvalues and eigenvectors of some certain matrices without any formulas or any algorithms. Well, differential equations are really important and they can explain lots of things which are around us. So essentially in physics, the differential equations are going to explain the many different physical phenomena. For example, if I would like to try to understand or try to simulate the movement of a pendulum, I need to solve a differential equation, it appears. So essentially, if I would like to try to understand how the angle of this pendulum, of this movement of the pendulum is changing, it's going to depend on the sign of this angle, it appears. So essentially the rate of change of the angle is equal to the sine of this angle. So you see, so this angle phi is participating in both of the parts of this equation. So if I solve this equation, which is called a differential equation, it's going to tell us the angle at every instant of the time. Well, it appears I can solve this kind of equations where the unknowns in both of the parts of the equation by solving them using this kind of matrix equations. So you see, so this is different than our previous equations. So we used to deal with, so it was ax is equal to the b, and we used to have only the unknown on the left-hand side, and we applied, for example, the Gauss-Jordan elimination method in order to solve the system, or we found the inverse of the matrix in order to solve the system, and so on. And all of these techniques are not going to work to solve this type of the system of linear equations or system of equations where the unknown vectors are going to be in both of the parts. So it appears we need to develop the new techniques in order to solve this kind of problems. And this type of the problems is called the eigenvalue problem. And I would like to try to understand essentially what does it mean. So let's look at this equation in more details. So let's say x is given some vector, and ax is going to be another vector, which is going to be parallel to the same vector. So this is what does it mean, this equation. You see, so if you multiply the vector x to the A, to the matrix A, it's going to be again a vector. And you see, so do you remember previously we say that, hey, if you are given two vectors which are parallel, then you can obtain the second vector, so this red vector, by just multiplying the yellow vector to some constant. So this is going to be our red vector, right? So essentially, they are the parallel vectors. And that's what this equation is going to tell us. So if you multiply the vector x to some vector, to some matrix A, it is going to give you some vector which is parallel to the x itself. Okay? So this vector, A times the x, is going to be parallel to this x. And essentially, this constant, which basically is going to scale this vector x in order to get the same vector as ax, is going to be called as an eigenvalue. And this kind of vectors, which are basically specific for different type of the matrices, are going to be called as the eigenvectors. So the word eigenvalue is coming from the German word Eigenwert, which basically means its own value. So essentially the own values of the matrices. And we will see later on in its applications. So their meaning is essentially the important values. They're going to tell us the most important values of the matrices. So let's discuss again a bit about the eigenvalue problem. So again, the eigenvalues or eigenvectors is such a vectors x so that when you multiply this vectors to the A, you are going to get a vector which is going to be parallel to this vector itself. So let's consider some examples. So let's say we are given the projection matrices. So previously we talked about the projection matrices. So we say that, hey, if you're given any vector B, and if you multiply this to some projection matrix P, it's going to project this vector P onto the subspace, right? So let's say we are given the xy plane, and we would like to project or find the projection of any vector onto this plane. So essentially, if you're given some vector B, by just multiplying this vector B to this projection matrix P, we can obtain this yellow vector, which is going to be on this plane. Well, the only question is, could you figure out the vector B, such a vector B, so it might be any vector B, so that the projection of this vector B is going to be parallel to this vector B itself. So let me write this. So what is the B? What's a B vector? So that its projection is parallel to itself. Parallel to itself. So far from this picture, it is clear that the yellow vector is not parallel to the blue vector. Well, if I would like to find such a vector B, whose projection is going to be parallel to itself, I probably need to choose this vector B from the plane. Well, the projection of this vector B onto this plane is going to be the same vector B. So let's say P matrix is going to project any vector onto this plane, xy plane. And in this case, the projection of this vector B onto this xy plane is going to be itself, right? So what is the eigenvalue in this case? So the eigenvalue in this case is going to be equal to the 1. And the eigenvector, sorry, is going to be any vector on this plane. Well, so we are going to have another vector. So here, another eigenvector. So can you just think about this problem a little bit in more details? You can pause this video and think about this in more details and figure out the vector B so that its projection is going to be parallel to itself. Well, probably I need to choose the vector B along the z-axis. Then the projection of this vector B onto the xy plane would be simply this point, or this vector 0 vector, right? And again, so if you are given the matrix P, which projects this any vector B onto the xy plane, and if you are given a vector along the z-axis, its projection onto the xy plane is going to be simply 0 vector. And in this case, what's going to be the eigenvalue? So the eigenvalue in this case, so let me denote this as a lambda 2, is going to be simply equal to the 0, right? So this is the factor which makes, so essentially 0 vector is parallel to any vector, right? And we can obtain this by just scaling any vector, by multiplying any vector to the 0, right? So this vector and this vector are equal, and the scaling constant is equal to the 0, which is the eigenvalue. So you see, so for this matrix, which projects any vector onto the xy plane, we've got two eigenvalues. The first eigenvalue used to be equal to the 1, and eigenvector is going to be any vector on this plane, xy plane. And we found the second eigenvalue. So the second eigenvalue is equal to 0. And this vector, eigenvector, is going to be on the z-axis. So we would like to try to reveal a couple of more properties about the eigenvalues and eigenvectors so that you will try to understand this a little bit in more details, a little bit in more deeply. So let's consider another example. So let's say we are given the permutation matrix, and we would like to figure out its eigenvalues and eigenvectors. So what does this permutation matrix is actually, if you multiply this P permutation matrix into some vector with the two rows, it's going to simply interchange the rows. It's going to be right, say y and x. Now, could you please figure out a vector so that if you interchange its rows, it's still going to be parallel to itself? Well, maybe it's going to be the same, right? So for example, it's going to be 0, 1, 1, 0. So what is this vector? So that if you interchange the rows, it's going to be the same vector as itself. So probably it's going to be 1 and 1, right? And this is equal to the 1 and 1 again. So you see, so it brought to you to this problem. So the p times the vector x is simply equal to the x, right? What's the eigenvalue in this case? So the eigenvalue in this case, so let me denote this was a different color. Eigenvalue in this case is going to be simply equal to the 1. And the eigenvector is this vector, 1 and 1. Now, think about this problem a little bit in more detail. So since this matrix is 2 by 2 matrix, it probably has a second eigenvalue as well. And what might be the second eigenvalue in this case? So probably, if I would choose 0, 1, 1, and 0, and the eigenvector as the vector minus 1 and 1, then by just multiplying this permutation matrix to this vector, I would obtain the vector by interchanging the rows, right? But you know this vector is parallel to this vector. We can even draw these vectors, right? So the minus 1 and 1 vector is going to be somewhere here. So this is the minus 1 and 1 vector. And where is going to be 1 and minus 1 vector. So 1 and minus 1 vector is going to be here. 1 and minus 1. So you see, so they are parallel because you can obtain the yellow vector from the green one by just multiplying the green one to the minus 1, right? So essentially, if you are going to denote this as a p, if you multiply this as an x, and what we obtain it is simply minus x, right? So this vector is simply this one multiplied to the minus 1. So what's going to be the eigenvalue in this case? So the eigenvalue, the second eigenvalue is going to be minus 1, and the second eigenvector is going to be this vector, minus 1 and 1. So this is essentially the eigenvalues and eigenvectors of this matrices. Of course, this is a way far away from the algorithms or the formulas which we would like to explain, describe, develop. So this was just a video lecture where I have tried to explain you the meaning of the eigenvalues and eigenvectors. So in our next video lectures, we are going to discuss about how to find the eigenvalues and eigenvectors algorithmically. So I hope that this video was helpful for you.